In this video, we're going to go over the paper called Panoptic Segmentation with a Joint Semantic and Instance Segmentation Network. The idea, roughly speaking, for this 2019 paper is to do a joint training of semantic segmentation and instance segmentation and use heuristics in order to combine them and obtain the panoptic segmentation results. Let's go through the abstract first. The key points here is that this is a single network method. And again, the idea is to combine the results of a semantic segmentation network and instance segmentation network by using heuristics that we'll talk about. It uses a ResNet50 as its backbone feature extractor. And this backbone is shared basically between the semantic segmentation and instance segmentation branches. It uses a mask RCNN type of architecture for the instance segmentation. And the pyramid pooling module is also used in semantic segmentation. The evaluation is done on COCO and Mapillary Joint Recognition Challenge 2018. Before we begin, in tasks like this, at a high level, basically labels can be kind of divided into two clusters. One of them is called things and the other is stuff. This is especially applicable for datasets such as COCO. If you think of things such as vehicles, persons, and furniture, these are called things, meaning that they are countable objects. The rest of the material are usually classified as stuff, meaning that basically the set of remaining elements that are usually not countable. An example is the sky, road, water, and things like that. Let's see an example and basically talk about what we mean. This here is an RGB picture. What you have here is a semantic segmentation, meaning that if you have certain classes, for example, car, tree, sky, road, things like that, at every pixel you have basically a color, or basically a class index. So you know, for example, this is car, this is car, this is car. All of these three pixels are going to have the same label. Now, as we talked about the things and stuff category of classes, here is a panoptic segmentation example. So here, basically, you can distinguish between elements by, their class. For example, this is trees from the stuff class. And at the same time, you can also distinguish between different instances of a class. So as you can see, the colors of different cars here are different. Accordingly, focusing on things only, this is going to be the instance segmentation, which is more focused on, basically is focused on things classes, things that you can count. So the idea in order to get to this is that you want to have like a class prediction for each one of the pixels, and you also want to have an instance ID, which for different cars, for example, could be, for example, 1, 2, 3, or whatever. It basically is just an ID, and for stuff, it is basically the same instance ID for all of the pixels. As we read through the method, again, remember that the main contribution of this approach is that the authors claim that they basically have used a single network to make panoptic segmentation predictions, which is kind of in contrast to the other works that have been discussed in the introduction as related works to this objective. Now let's talk about the methodology. As mentioned before, the base of this network is a ResNet50 feature extractor. So, for example, you can see here, you feed the RGB image to a ResNet50 to obtain the auxiliary features. Then, there are two branches of computation. One of them is the semantic segmentation branch. In that one, you first have a pyramid pooling module, and then basically you upsample it to reshape the prediction to the same dimensions as the image. This is done by deconvolution and then by bilinear interpolation in resizing the predictions. Then there is the instance segmentation branch. First, you have a region proposal network to basically obtain region proposals based on the mask RCNN framework, and then these features also go through the final layers of ResNet. In the instance segmentation module, you're going to have a classification score as one of your outputs, bounding box coordinates, and also an instance mask. There is a non-maximum suppression applied, and the output would be basically pixel clusters with class labels and the identifiers for different objects. Now when it comes to optimization, there is basically this linear combination of them, with these lambda values controlling the contribution of each part of this loss to the final objective. So first thing, you have LRPN OBJ, which is the softmax cross entropy objectness loss function for the region proposal network. And you also have the L1 regression loss function for the region proposal. You have the softmax cross entropy loss function for the object detection. You have a smooth L1 regression loss function for object bounding boxes. The sigmoid cross entropy on instance masks. And the sparse softmax cross entropy segmentation loss. And the last one is the L2 regularization. Now let's discuss the merging heuristics. There are two main problems that the merging heuristics is designed to solve. One is the overlapping instance masks. So let's look at the instance segmentation module. Doing a naive non-maximum suppression on the overlapping instance masks is not going to have a good outcome because many of the true predictions will also get removed. The heuristics used for this case is that when two or more instance masks predict a certain pixel that belongs to them, basically to their object ID, the pixel is going to be assigned to the instance mask with the highest probability at that pixel. The second problem is conflicting predictions for things classes. The solution they propose is this. First, they look at the semantic segmentation output, and then they remove all things classes from them and replace them by the most probable stuff class. And then on whatever pixel things are predicted in the instance segmentation module, those basically will replace the semantic segmentation outputs. And there's also this other heuristic, which means that any predicted stuff class with a total pixel count of below this number is going to be removed and replaced by the next best scoring stuff class that has been above this threshold. In terms of implementation, the momentum of 0.9 was used in a SGD optimizer format. The rest of the implementation details are elaborated upon in the paper. The most important part is basically this part about the contribution of different loss components, and table 1 with regards to their results on COCO and MV datasets. One other key detail is basically this ablation study, showing that each one of these two components alone contribute to a good Panoptic quality score, and the joint training is going to elevate that to a higher one. And they also have this problem in detecting small objects in the MV dataset, and based on some empirical studies, they mentioned that it's basically the region proposal network that basically causes this bottleneck, because only a small portion of these objects are actually covered by the region proposals. And that basically concludes this paper.